Yes, that.
Okay. Okay.
Hey, doctor, you hear me? Doctor, you hear me?
Good evening, sir.
Good evening, Anna. You come the last day. It's good. At least this one want to treat now is a fresh. This one now is just a fresh one. So
Yes, sir.
the other one may be confusing, but this one want to talk now is a fresh one. You can
Yes,
grasp it
thank you,
because
sir.
the other one it will be difficult because if you are not here from the beginning. Okay. As everybody come back, you know some people find difficult because of network to connect back. Somebody's end is making noise. Okay, Jane, you are connected. That's great. Yes. Let's quickly look at the non-parametric test. You know, as we all know, sometimes data set do not meet the assumption required for parametric test to be carried out. And I want to assume that we know those conditions. And it is not possible to correct for the problem of the distribution through transformation of data or use of robust tests. You know, if you remember, I talked about three things. If a particular data set does not meet, is not normally distributed, what do you do? If you cannot assume that it's normally distributed and there's homogeneity of variance, what will you do? You can, there are three things. You can rely on the robustness of tests, you can transform the data, you can use non-parametric tests. Robustness of the data of the test is relying on the robustness mean that that particular test can still be valid if not all the requirements for parametric tests are met. Like there are some robust tests like ANOVA tests, they are considered to be robust in certain conditions. So if you cannot rely on that robust, you have to, and it's better not to transform. It's better opt for non-parametric counterpart. In this scenario, we use special kind of statistical procedure called non-parametric tests. They are sometimes known as assumption-free tests because we make few assumptions about the type of data which they can be used. No, it's not like, is it distributed? Is it homogeneity of is it normally distributed? Is there homogeneity of data? Is this, that? No, too many assumptions. So because you don't make, you just go ahead and do your test. They call it the assumption-free test. Most of the non-parametric tests work on the principle of ranking. Ranking is, most of them is ranking. Finding the lowest score and giving it a rank on Y. Then find the next higher score, give rank of 2, and so on. Usually start from 1. So if there are 80 samples that you rank 1 to 80. Now, the process results in high score being represented by high rank, while low score are being represented by low rank. The analysis is carried out on the rank rather than the actual. That's one of the drawbacks of non-parametric because the analysis is carried out on the rank, not on the actual value of the data. It's the rank you give them. Now, example of non-parametric tests. Do I try to put both the one you use for comparing two means and more means? Wilkinson ransom test or Mann-Whitney test. We use it when you are comparing two mean independent groups. If it's that is the non-parametric counterpart of independent t-test. The example I put here is example of parametric test useful to compare means. Now, Wilkinson sign rank test the means of different in pair observation. All this one we have done them in our workshop on comparison of two mean, t-test and the non-parametric.
1 month ago.
Now, the one that concerns on number 3 and 4, Kuka-Wallis one-way ANOVA compare means of more than two independent groups. We are going to look at this. Friedman two-way ANOVA compare means of more than two independent. So this one is like for factorial ANOVA, two-way ANOVA. This one for one-way ANOVA. Kuka-Wallis is the non-parametric counterpart of independent one-way ANOVA. Like if you want to use, like for that placebo, this our Viagra data, if there is no normally distributed, we want to use non-parametric counterpart, we now use Kuka-Wallis test. Like the Wilkinson rank sum and Mann-Whitney test, Kuka-Wallis test is based on rank data. We simply order the score from lowest to the highest, ignoring the group to which the score belongs, and then assign the lowest score a rank of 1, the highest score a rank of 2, and so on. You see, you just rank irrespective. Maybe there are 3 groups or 4 groups. You just rank all of the irrespective of the group. Of course, now different rank will form in different groups, so you now add all the ranks together. You like the what we did in Wilkinson ransom and Mann-Whitney test. After ranking the data, we collect the score back into their group and add up the rank for each group. The sum of the rank for each group is denoted as R. Is used to denote circular. Well, it's supposed to be high. Don't worry, it's small I. This is Joseph Kruka. So it's one of those people that develop it. It's a Kuka-Wallis. Another person is Wally. This is Kuka. Now we have a data set here. These data sets try to see effect of soya meal on sperm count. Soya meal. Soya. So there are some people, we have the sample size here is 18, 20, 20, 20, 20. We have one group, 2 of them, no soya milk, no soya food and milk. Then 1 soya meal per week. This one's 4 soya meal per week, 7 soya meal a week. After a while, you try to check their sperm count. So what you are seeing here, the sperm count at this first column of each of them. Sperm counts. In millions, oh sorry, it's on the in millions. In millions. So the person that brought the data says it's a fictitious data. He said the doctor, the medical people should forgive him because the sperm count are lower than how it's supposed to be. Just a fictitious this data. So the test, if you look at it now, what we have been done here is to rank the smallest. If you look, the smallest one here is 0.31. Can you see? So that's why it's number 1. This is number 2. You may find number 3 somewhere. Number 4 is here. So the rank you give to this lower or to the 80 will be this one is the highest value. 31 point this is the highest value. That's why it's number 80. So any value rank can fall in any place depending on which one is higher than which. So it's like the smallest among all give 1. Search for it. So this one is not difficult to, you can be like, if you want to do, you can be sorted on Excel. It can be sorted on Excel because
okay. Sorry, sir.
Yes?
Okay, so if I may understand your explanation,
Yes.
you are saying that for no soya, one soya meal, you collapse everything together, you sort in ascending order and assign ranks.
Yes.
Okay.
Yes. But you see, even though you do that, you still have to know each of them, which group do they belong to. You must be able to recognize it.
Okay. So, okay.
And that one can be done like in Excel now. We can do this in Excel now. If I put in Excel now, it's just a matter of group 1, the group 1, I will give them 1 to 20. Group 2, I will give them normally, the way it's arranged now. I will number them 1 to 20. Group 2 will be from 21 to 40. Group 3 will be 41 to 60. Group 4 will be 61 to 80. Now, this rank will be a separate column. If I sort by rank, you see it. So you will see the way it is that if you, even without rank, if you sort by the value, the original value, it will follow this rank. It will assign your rank. If I now want to put it back here, I sort by the original numbering, it will give me, I'll be able to put it here. I don't know if you understand me now, the way it is, it has been done.
I get it, sir.
Yeah, so it's just a matter of giving the rank. Yes, you have gotten it. So 1 just happened to, this is the smallest of all of them, 80 something. And this is the highest. And that's why it's number 80.
Excuse me, sir.
Yes, sir. Go on.
Is it a Z that we're going to use to rank it, to do the ranking?
Well, in a big something like that, for you not to make me say waste your time, that will be the best. But if you, for smaller data sets, you can see it there. But anyway, physically, the computer will rank it. We are not ranking it for computer. This one is just explanation how you can analyze with your hand. In the real life, now the computer does it for you. Don't even rank it. What concerns you? You just enter. You're going to see when you open the data. There's nothing like this thing. But the computer will rank it and do the work. But it's when you want to calculate with hand, you do the ranking with hand. And we are doing that so that we understand the logic. Understand the logic behind it before we now run it with SPSS. I don't know if you understand. Or you want us to do it with, okay, you know what? Let somebody who has the data set. Everybody has it now. Everybody has it.
Please, sir.
What should I do it with Excel now?
Isn't it just to sort in ascending order? In ascending order.
Yes, now.
Ascending or descending?
Yes, it's sorted.
No, it will be ascending because you're going from the lowest. You're picking the lowest to the highest, isn't it? Yes, it will be ascending now.
It's ascending. Okay, don't worry. I don't know. Okay, don't worry. This issue should not cause much problem. I will do something. I will do something now.
That's the new one I wanted.
Don't worry. Don't worry.
It's not arranged in a particular order.
No, I will even do it now for you. Don't worry. Because I want you to understand it. I want you to understand it. It's the logic. It's not a big deal. So, I will open Excel now. Just a minute. Ukawalis. Can you see the data set I put in Excel? Can you see?
Yes.
Can you see? Can everybody see?
Yes.
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 Yes. Okay. Yeah. This is data set. If you look at it along the Excel something now, what I want to do here now is for you to, I want to remove those ranking out. The part that is ranking, I want to remove it. So, and see the way it is originally. So there are 4 groups. These are the 4 groups. These are the value. So from if you want to really do it so that you won't make mistake, what you do is that somebody is, Prof, this is making.
It's not from.
They have muted you and it's okay. Who is? Okay. So if you want to, what you do now? So this is exact numbering. You need to put number, or else if you don't put this number there, if you go and sort it according to, you may not be able to know where they are from. You understand now? So what I'm going to do now, put number from 1 to 80. When you put number from 1 to 80, so the first group is number 1 to 20. I call the second group 21 to 14. The third group is 41 to 60. Then the last group, group 4, is 61, 80. Can you see now? Now, so this is the original, the way they are arranged here. So that was to preserve how they were arranged. Can you see that numbering? Don't rely on the number on Excel, because if you rely on the number of Excel, it will not do that one for you. So I've already, so that I preserve the way they are, right? Now, all you need to do now, the value itself, you now sort. You say sort under home. Sort smallest to the largest. Can you see now? It has sorted it. Can you see? It has sorted it from the, if you remember, that the number 80 was that 21, the highest. It has sorted from smallest to the highest. After you do that now, you can now give the rank. Just do this one. Just draw this one and Excel the way it is. That is the rank. Can you see now? That is the ranking. So you want to get it back to the way it is originally in the. So you come and sort the serial number. You need to look at it before. Under home, you just say sort. Can you see? It has returned it back. Can you see? So this is what you see there. So that is just the logic behind it. But it's bringing this 61. Why is it bringing number 61 this place?
That's what I was wondering myself.
Yes, because that's the only problem here. That's number 61 to be number, because this one was number 61. So otherwise, that is just an error here. But you can see this sorting now. Can you see? So I can now go and put it now and go and place it on that place with their ranking, just to place it with their rank. It doesn't really matter. It's just for you to conceptualize it, because you don't need to do all this one. It's just to enter your data. The computer does the ranking. All this have been programmed into the computer to do the ranking. I think we understand that now. Let's proceed. Now, after that, the test is this the formula for the test. 12 all over, so that how they derive this thing. So that you don't even know how they derive it. Just 12 all over m plus m1 all over this. So R1 just means sigma R square. That is the group, the sum of rank of each. You know, when you rank, you have to sum. Look at the sum of the rank of each group. You sum. If you sum all this one, it give you this. Each group, the sum of the rank. So R means the sum of each rank of each group. So what you do now, sum of the rank, square it over the sample size. Each of them have the same sample size, 20, 20, 20, 20. And you see, that's what is in the formula here. When you have done this, you have divided this by this. This 80, n mean sample size. 80 plus 1, 81. When you do that, multiplied by this one, you now remove this from it, give you 8.6. This is the statistics. The test statistics arc is a chi-square. And this is a chi-square. What you just is a chi-square. It follows chi-square distribution with the degree of freedom of how many group? 4. 4 minus 1. The entity minus 1. So k minus 1. K here is 4. The degree of freedom is 3. So let's run it now. This is how to run it. Let somebody share and run. Soya, you see soya. There's data says soya. Who will share? Who will share with us? Soya. Shegun, can you share today? Shegun. Shegun.
Yes, sir. Yesterday I explained that I'm using.
Yeah, you see your computer. Okay. Okay, who will share? Jane. Jane, can you share? Soya.
Okay. Let me open the file.
Once join, yes, you can just open it and share with us.
Okay, sorry, I'm trying to download it from the email. Just give me.
Oh, you have not done it. Okay, Baba Gana, do you have it? You can share if you have it. Dr. Baku?
All right, sir.
If you have it, just share. That is Soya. That is the name of the file.
So, are you there?
Yes.
Are you there, sir?
Okay, I'm there. I'm coming. Okay, yes, you can see it. Great. Now, if you look at it, they just Soya. This one, if you go to view, and click on that view, that value label, uncheck that value label, and you see,
yeah.
Group 1 was the none. Group 2, 1 mil. That's where the label is here. So just just show. So can you see the value? So the rank is not here. Just for you to, if the computer that will do the rank is for you to know the logic. But the computer is the same logic computer is going to use. They will do the rank. They have already programmed it. Okay, analyze. Go to non-parametric. No, it's non-parametric we are doing. Non-parametric down.
No, it's non-parametric, yes.
So in this case, the computer has already ranked it.
No, it is when you are running it that it does not rank it. Because if you are running, you will see it. But the computer, when you give the command, it is mathematics that they have already programmed it, you will rank it. It's when you are running it that the computer will rank it. Do you get it now? We go to legacy dialog. Legacy dialog. Go to that legacy data. There's an arrow there.
Yes.
Non-parametric
Yes.
legacy data. Go to K independent sample. K independent sample. You know there are 4 independent samples now. There are 4 groups. K independent sample.
Yes.
Click on it. Yes. So you move the swam can to the list variable. Then the other one, number of soya milk, as the group variable. So define group. Minimum. Minimum is 1. You know the way you rank the group, 1 to 4. Maximum is 4. Means that you have 4 groups. You will see. Click continue. Go to exact. Yes, you can use it. If AC20, you can leave it. If you want the p-value to give you the confidence interval, you can choose Monte Carlo, but just leave it. Just continue. But if the sample size is very small, we usually click on the exact. Just like the way we do exact.
So what does asymptotic mean?
Asymptotic, well, it's just like the question I asked yesterday about Togona. And I will remember even tell you. So, well, I don't know what they mean by it, but what they just mean here is that if you don't want to just a normal, you don't want variation. If, like for this exact now, if the sample size is very simple, is very small, you use exact. If you want to large sample size, but you want the confidence interval, you use Monte Carlo. But normally the institute is the normal, the p-value you give to us. Just continue. Then continue. I will come back and explain that orthogonal for you because I tried to check it. Then click on option. Click on descriptive. And click on quartile. Quartile. Those on the addition, they are not part of their more information you give you. Continue. Click continue. Now, you will see that by default, it has checked Kruka-Wallis. You know,
Yes,
median, click on median. Median also, I will tell you, you know, when we were comparing, we use median, we say that median test is non-parametric counterpart for both t-test and ANOVA. No, we use those that were in the training. We use median. I will explain the way it works. Yeah? If you want trend, click on Jokere's Dapstra. That's for trend. Because go to look at the result. Click OK. Somebody's is it Jane something that is making noise? No, it's not. It's not at home. Okay. Can you see the results?
Yes.
Somebody's background is making noise. Please, somebody's background should mute. Somebody should mute. Dr. Babagana is okay. Don't worry. I know what to do.
No.
Even Prof to mute Prof is difficult. He doesn't mute. Okay. I think the noise has stopped. Okay. Look at it. This one just telling you the number in this category. Go down, scroll down. No, the description you did up here, look at it, the first table, show you the mean, median, standard deviation. Can you see? Let's continue. Let's see. Look at the median. If you look at it, it's far away from the mean. The mean is 3.8. No, yes. The mean is 3.8. The median is 2.2. It's far apart because this is 3.8 million, 2.2 million. No, the difference is much. So then we have the percentile. We use 25 percentile, 75 percentile. So you can see the median, and it shows that it is not parametric. You should use number because it cannot be normally distributed with this. So that justifies the use of the non-parametric. Let's go down. Look at the Kukawalis. Is a chi-square. Is chi-square. If you remember the value we got is 8.659, and the degree of freedom is 3. Look at the p-value, 0.034. It's significant. So what it's telling you is that the values, if you look, I think there's a place that shows the mean for different groups. Let's look at the mean for different groups. Where is the mean for? Under that descriptive, is it not? Okay, this is the median test. This is the median test. But the funniest thing, wait, don't scroll up small. Look at the median test now. Let me explain the way the median test work here. So, okay. If you look at this table, the first table under the median test, you will see sperm count in million. You see the first one greater than median. The second one less than or equal to median. What the median test does, and the way you do it is that you look for the median for the whole, you combine all the 80, you look for the median value. So any value for each of the group now, you know you count. How many value for no soya milk group is above median is 12 of them. 8 are either median or below. For one soya milk, is 11 that are above the median, the remaining 9 here. The other one is 11 that are above the median, the remaining one here. In this last group, is 6 that are above the median and the remaining one. So this one now, you calculate the chi-square. This is, it gives you 2 by 4 table, and the degree of freedom is 3. Because 2 row, which is 2 minus 1, 1. 4 column, 4 minus 1, 3. 3 times 1, 3. The degree of freedom is 3. And that is normal Pearson chi-square. You can just draw it. Can you see? Normal Pearson chi-square, it give you. Look at it. So you will see that for the same data set, median test is not significant. Kukawalis is significant. We said it before when we were doing this training on the comparison of mean, that the median test is not as powerful as all those other tests, Wilkinson, Whitney, and Kukawalis. The power is not much. So sometimes something, the difference may be there, we will not get it. The only good thing about the median test is that it has no second when it comes to survivor. If it is survivor, any data that is sensor, when you say sensor, it's in survivor analysis, you say sensor data. When the variable of interest is time before an event occurs, that is in survivor analysis. That is where median test is more useful. You can only use it. You cannot use all this Whitney, all those Kukawalis. You cannot use it. It's median test you can use. Okay, scroll down. Scroll down. Dr. Baba. So I talk about trend also. This one measure the trend. The trend means that the trend in the median rather, along the 4 group. You know, this soya mean, then 7 mean. If actually the soya mean reduce sperm count, the sperm count should be lowest with the one that have 7 mil, followed by the one that have 2 or 5 mil, then followed by the one that have 2 mil, 1 mil or whatever, and follow the one that should have the highest should be the one that has no mil, soya mil. If actually the thing reduces sperm count. So what John Tapras test is doing is to look at the trend. Is there any trend, increasing or decreasing trend in the median of the groups we are testing? So if you look at it now, it's significant. Because if you go and show the, okay, you can stop sharing. Stop sharing. Yes. Let me just, I don't know if there's any question concerning this one. We just explain now. Okay, see that.
I've been battling with network one after another. So
okay. Sorry for that, sir.
Cut off. It's a very embarrassing situation.
Yes, you have a question, right?
My network was just off during the running of the test per se.
Okay. So you want him to rerun the test?
Oh, I wouldn't mind if it's possible.
So, House, you agree with that? Consensus? Another way you can run because I have the house.
I agree with him.
Okay. So, Jane, have you downloaded it now? So, since you agree, you should run it.
Yes.
Okay.
I've downloaded.
And let me stop sharing. So, yeah, share now and run it. Let's run it. Share. So, you downloaded, you know where you save it.
Yes.
Okay. Share with us.
Okay.
Dr. Balogun, you don't, Dr. Balogun has been out since.
Okay, so can you see my screen now?
Yes, you can see.
Okay.
So, go to Prof. Say you are following. Go to analyze. You can see. Wait, no, because
Yes.
Wait, Jane, wait. Because there are 4 independent groups. They are different groups. That is, the people in group 1 are different from group 2. So they have to be entered in series. In series means that one after the other. If you look at the way we coded down, so the first group, no soya meal, is coded 1 to 20. The second group is coded 2. That's 21 to 40. The third group 40. Is coded 3. That's 41 to 60. Then the last group is coded 4, 61 to 80. And now put their count down, just follow like that. So you see, you're going to see now, because the next one we're going to do now will be in parallel. This one is a series because there are 4 independent groups. Yes, you enter them one after the other and give them the serial number. Okay, go to analyze. Go to analyze.
Parametric.
Non-parametric. Down.
Yeah. Kruskawalis.
2 independent sample, yes. You have done it now. Wait now. If you have
already
done it,
there.
It's already there.
Yeah.
No, I was following, but at some I got lost at some point.
Okay, click on option. That's the only
Option.
Option.
Well, it's
already... Click on descriptive. You didn't click on descriptive.
What about the quartiles?
It's okay. It's okay. We did it. We checked it that time. Don't worry. Okay, continue. Okay. So we say that this is Kukawalis. We also do median. If you remember when we're doing comparison of 2 means, when we did 2 tests, the workshop on t-test and non-parametric counterpart. We say median test is one of the non-parametric counterparts of independent t-test. And it's not only for independent, it's for both for t-test and ANOVA. Can you see now? So he compare 2 or 3 or more mean. That's one thing with median test. He compared 2 independent or more means. So it's both useful for t-test and ANOVA, and we use it for the for comparing 2 mean. It's a non-parametric counterpart for t-test and also a non-parametric counterpart for ANOVA. So when we're doing that t-test, we did it, and that's why I click it here. The result here, I explain the logic. Then this one is the trend. This Junker Tapstra. This test is for trend, because you have, like this one, we have 4 groups. We expect, since the factor we are looking at it is ordinal. It's ordinal because the soya meal you take is in order. No soya meal, 1 meal, 3, 4 meal, and 7 meal. You see, it's in order. It's ordinal scale. So we want to see trend. Is there any change? Is there any linear change, trend in the median of each group? That is what this, just like the way we do chi-square for trend. the same thing that this one is doing. So click OK. Click OK. Have you clicked OK? If you have done that, share your screen because we can't see that. Go and second new share. Share the result with us. Oh, I should share my own because I have the result on the slide. Since it's taking time.
Share so we can get on because of time.
Okay.
Okay.
Going to 8.
Okay, let me just stop sharing. I will share. I have the result already. I have the result on the slide already. It's just the process, the step in running it that.
Which we have got now.
Yes, yeah. So these are the results, I think. Yes. Okay, the descriptive. Okay, this one I didn't put the quarter here. Anyway. Then look at the rank. Okay, this one is not. It's just the mirror. That's why I don't know the use of the mirror. Look at the Kukawali statistics. It's a chi-square. If you remember the one we calculated, we had the same value, 8.659. And the degree of freedom is 3 because there are 4 groups. 4K is 4. The degree of freedom is K minus 1. Number of group minus 1. So then the p-value is here. It's significant. So if you go to
Monte Carlo.
Post-op, sometimes if you now, I will see, don't worry, I will, the other slide are there. When you do it, if you find different now, where does the different lies? Does the different lie between group 1 and group 2, group 1 and group 3, between group 1 and group 4, or between group 2 and group 3, or between group 2 and group 4, or between group 3 and 4? There are 6 ways you can pair 4 things. Where does the different lies? You won't know. But it's not as straightforward. The post-op test is not as straightforward. There are 2 ways of doing it. They are so somehow. If you have to now do Mann-Whitney test, which is to compare the 2, if you have to do it for, let's say you do it for those 4 of the 6 of them, you have to divide your 0.05 by 6. That would be the level where you reject no hypothesis. You may decide to do it like this one. You measure test soya meal per week compared to no one, or test 4 soya meal per week compared to no meal, or test 3 soya meal per week for no meal. You may compare each of them with like a placebo now. If you do that, you have done 3 tests. You have to, if you do the 3, you have to, but to me it's rubbish. You have to now divide 0.05 by 3. When you divide, that will be your level. It is when your p-value is less than or equal to this value, you can say that the thing is significant. Can you see? If you do this, if you decide to do 6 tests, you have to divide by 6. Because after all, that's what Benferroni does. Or another way, this one is complex. You look at the difference between the 2, the rank, the sum of the rank. Maybe you pair them, like between 1 and 2 group now, the sum of rank. You now say alpha. Your alpha here is, you choose alpha at the level of Z alpha, at the level of 0.05, divided by, there are 4 groups. 4 times 4 minus 1, which is 4 times 3, 12. When you now multiply 0.05 by 12, it gives you 0.47 something. You now go and look at it in the statistical table, the number, the value, the Z, the corresponding Z is around 2.26 something. You now multiply by this, this N is the total sample size, which is 80 into 81 divided by 12, 1 over, all those complexity. That will give you 2.29. So if what you calculated, if your difference between the two mean is greater than this, on this side of the equation, that shows that it's statistically significant. It's a little bit complex, but that one, you cannot run it. It doesn't run in, maybe later we will put into their computer to run it with SPSS. So the post-op test, that one, just forget about it. I don't even want, because it will raise a lot of questions. Just leave that one. I put it there. Not that some information for academic purposes, because some people are very, it's in the module. You can read it if you can understand it, but don't bother yourself with it. Not many people do that. Now, the one I say for trend, you just want to check it. Is there any trend? You can see that it shows that if you go back to the table that shows their mean, the mean, the original, okay, the original, that did I put the mean there? Okay, didn't put the median. If the median, we calculate the median for each data set, you expect the median to follow a linear trend. Of course, if you look at it, the median for the low soya would be higher, because after all, that's where you even have the highest value. So what this one is telling us is that there's a trend. The trend is significant. Look at the p-value. The trend is significant, 0.013. That is, as the number of soya mean increases, the median sperm count reduces. Then the last one is the median test. No, you can decide to carry out median test, or you carry out Kukawali. No, I just click on it the other time. The way I will have illustrated it on the slide is the way the table it gives out. That particular data, what will happen is that the overall median, when we calculate the overall median, which is 2 point something, we now look at how many in this no soya mean have value more than you put it, you count 12 of them. Then 8 has equal to or less than the mean. For one soya mean per week, how many? 11 have above median. 9, the remaining 9 here. 4 soya mean, 11 have above median. The remaining 9. Know that each of them is 20, 20, 20. The 7 mean per week, 6 add above median. The remaining one here. So this one now, it forms a 2 by 4 table. I calculate the chi-square, Pearson chi-square. If you do that, if I can demonstrate with you now with WinPepi, it will give you the value. You see exactly. Look at the chi-square now. Chi-square chi-square is 4.4, and the degree of freedom is 3. Of course, row minus 1 times column minus 1. We have 2 rows, 2 minus 1, 1. 4 column, 4 minus 1, 3. 3 times 1, 3. The degree of freedom is 3. The p-value is 0.221. To confirm that, let me just do something now. Let me share WinPepi with you. Can you see the WinPepi now on the screen? Can you see? Somebody should talk if you can see. Hello? You can see, okay. So, I stopped. Why did you stop? Nonsense.
The output of the Kukawali is.
Okay, is the output you are seeing? You are not seeing the WinPepi.
We don't know.
Oh, there. The WinPepi has come up now.
Okay. So, if you remember, it's 12. The first one was 12, 8. 12 above the mean, 8 not above the mean. The next one is 11 stroke 9. The next one was 11 stroke 9. The next one was 6 stroke 14. This is the way it is. If you run it, can you see? Can you see Pearson chi-square? Is it not 4.4? And the p-value is 0.221. Is it not the same thing there? And the degree of freedom 3. Is it not the same thing on the screen? In the results, that's the same thing. So just to confirm. So when even you yourself, that's how to calculate it, even without a computer. You look, when you know the median, you arrange in ascending or descending. The median value, how many is above the median, how many below, how many is for each of the group, you arrange in table like that. You calculate chi-square. That is the median test. You can see the median test is not significant. For the same data set, and Krukawali is significant. It shows that the median set have little power. It's not as powerful as Krukawali to detect the difference. Do you get the logic now? So any question on that, so that we move to the next one, which is Friedman ANOVA. That's the last one, because that's the one that do two-way ANOVA, the non-parametric counterpart of two-way. Any question on this?
Go on.
That's great. H, yeah, Friedman ANOVA is a non-parametric counterpart of one-way repeated measure. When we say repeated measure, it is, even though when you say one-way repeated measure, the one-way repeated measure is a factorial ANOVA. It's under factorial. That is one factor, but you do it 2 times. So it introduce 2 factors in. It is used for testing difference between conditions when there are more than 2 conditions and the same participant have been used in all conditions. It is based on rank data, the same. We rank the data for each person and all the rank for each condition. Look at an example, just straightforward example. 10 women who consider themselves to be in need of losing weight were put on a special diet for 2 months. Their weight was measured in kilograms at the start of the diet and then after 1 month and 2 months. These are the weights, 10 of them. As you can see, number 1 to 10. Look at their weight at the start. This is the weight. After 1 month, these are the weight. After 2 months, these are the weights. So you now rank them also. Start 1 month, 2 months, you rank them. What you are ranking, you are not ranking vertically, you are ranking horizontally. For each person, this person, number 1, maybe is Eunice. You want to rank, which one is it? You have to rank. So the smallest weight here now is the start, followed by this. That's why it's a 1, 2, 3. This one also, 1, 2, 3. The smallest is this one, this second, third. The same thing with this one. But when it comes to this one, the highest is at the beginning. And you see, so this is 3, 2, 1. This is highest, this is number 2, this is number 1. So if you have to rank now, this is the smallest one, the third, second one. So this one, 1, 2, 3 also. This one is also 1, 2, 3 from the rear. Can you see? So that's how they rank everything. So when you do that, you now add the rank. You add the rank. So if you add the rank now, this is 19, 20, 21. So the logic behind what we want to do now is that this test statistic is this. Don't mind them, this one just means 12 all over n. N is the total. N total here is 10. K, number of conditions.
Groups.
Yeah, thank you. Number of groups. That is condition. That is what you mean by that one. That is 3 measurement samples. First start 1 month, 2 months. So K will be 3. This one means sigma, addition of their sum of the rank square. The 3 rank, then minus 3 n, which is 10 here. K plus 1. Sum of the rank for each group R. Then total sample, number of conditions. The test statistics is a chi-square also. Can you see? The degree of freedom is 2 because K, there are 3. Start 1 month, 2 months. So 3 minus 2, 3 minus 1. When you put it here, the answer is 0. You know this type of thing, you know that it cannot be significant. If the chi-square ends up to be 0 with the degree of freedom 2, you know the critical value for chi-square degree of freedom 2 is 5.7 something. So you know that the weight reduction, the diet didn't do anything. So let somebody run. Let somebody. Who will run it? These are the
Willow. Let Willow continue.
The Willow didn't run anything since. You see, it's only law. It's only law. Jane only law that did the other one.
Well, I thought it's Ugonaya that have been running.
No, it's Jane. It's not Ugonaya.
My system.
Okay, Jane, you can, if you have it. No, some people they are using phone. They are using.
I'm using both phone and computer and everything. It's very.
But you didn't want to run for us, sir.
I can't access anything. I use phone. I use 9 Mobile. I use the Tate Salad. I use MTN. Nothing is steady.
Okay, Jane, will you share with us? I think it's diet and weight, something like that. The name of the file is diet and weight. I don't know if you have it. Hello, who is there? Because you running it is part of it. Dr. Bako, will you do it for us?
Okay, I'm here, sir.
Okay. So share the data with us. Is weight and diet and weight. The data is diet and weight. That's the name. Okay, that's great. Okay, that's great. You can see that this one is arranged in parallel. Can you see? It's not in series, not one after the other, because the three groups of measurement are from the same people. They are not from independent.
Different.
Yeah, that's why it will be in the front of each other. You have to arrange it. You have to enter it in parallel.
It's like the paired test.
Exactly. So the only difference is that if it is 2 now, it's t-test. But once it's 3, you are in it's not t. Okay, now go to analyze. Non-parametric capacity. Legacy dialogue. K related sample. Down. K. You know the other one is K independent sample we did, but this one is K related sample. Yeah. Click on it. Just move all of them. Control A and move all of them inside. Just Control A. Okay. Great. You can check the statistics. What is it right here? Click on the statistics. Statistics. Put descriptive quartile. Just click on them. Continue. Click OK. So you have to share. We know that that's the way your computer behaves. It's showing us this one as if you didn't click it. So I know that it has run it.
Okay.
Share.
Okay, let me.
New share.
Okay.
We have gotten you to your computer.
Let me. Where's my output?
So you have to new share for us to. It's not sharing.
It's not sharing, no.
So you go to share screen now. When you click on share screen, that output you do double click on.
I'm looking for the output. I'm looking for the output.
It's there.
Interface.
It's there. Maybe you open too many things. When you open too many, you won't be able to recognize which one.
Yeah, I'm working on a lot of things. Really. Okay,
Yes, we have seen it. You can see if you go down here, you see chi-square 0.2. That was what we got the other time. That's why the p-value, the degree of freedom is 2, k minus 1, which is 3 minus 1. And look at the p-value, so big, 0. Which one are you showing us down?
Sorry.
Scroll down. This one for the last one.
Yeah.
The screen has disappeared though. You can see the output.
I unshared so I could go to the current one we're working on.
No, even that one is shown now. It's just the last. If you scroll down, it's the last one. You want to run it again? Yeah, showing all the data editor window. New share.
Rerun.
The result. No. If you rerun also,
Okay,
you go to, no, don't rerun. It do the same thing. If you rerun,
Rerun.
I can share my own. I don't know. Do I
Please
even
let
have
her rerun.
No, it doesn't. That one doesn't make any difference. If you rerun, okay, I have the result here. Don't worry, I've shown it. Can you see it?
She's almost there. She's almost there.
Okay.
She's almost there.
It's there. Just okay it.
Okay, okay. I've closed. Okay.
Okay.
Did you click statistics?
Just click OK because everything has been clicked. Just click OK. Just click OK. Everything has
can you click?
I think you have to share
unless you share the screen with us, you share the output with us. You have to share it separately. Go to new share up. Go the icon is up, new share. You will click on it, you look for the output is different. You double click on it.
Okay, new share. Wow. Okay.
You can just unshare because I have, okay, yes, that's great. You can see now.
It has come out.
Yes, I've seen it.
I've seen it now.
Look at the last table there. Test statistic, chi-square is 0.2. That was what we got in the calculation. And the p-value is 0.905. It's not significant. You can see, yes, you can see the weight now and give us the mean weight, different months, all those. That's all. That's all. Any question?
Yes.
Yes, okay, go on.
Yes. Yeah. I'm just wondering why maybe it's just for purposes of illustration.
Okay.
Weight is numerical.
Yeah.
And we can imagine that probably the distribution follows normality. Mm-hmm. So is it not more appropriate to use a parametric in this kind of weight thing? Okay. I tend to associate non-parametric essentially with things that are ordinal, nominal, and but these are weights that one can do with parametrics.
Okay. Yes. Whenever something is ordinal, you say nominal. You cannot even do anything. You cannot compare means with ordinal because with nominal because you cannot give value to nominal. It's ordinal you can give numerical value to. So we know that when it is ordinal, it's more appropriate to use some parametric. But even something that normally follow normal distribution, in your data set, it may not. You may run it, when you do your descriptive statistics, you discover that it's skewed. You're like all these cases. Now, if you look at, if you go and do the mean and median, you check the, okay, look at the median, look at it. Look at this descriptive weight as start. The mean is 78. And the median, look at it here, the under 50 percentile, 69. Can you see the difference? Can you see?
Yeah.
So the difference is 78 and 69. You see, it's much different between mean and median. That shows that there is a positive outlier. So the mean is bigger than the mean. For that first, the start. For the second one, the mean is 77.46 and the median is 68 also. So the mean, there's positive outlier also. Then the third one, the mean is 77, the other one is 72. This one is even the one that is closer, that is better. The last one, 77, 72, but they're still different. So, you know, from that data set, you know that it's skewed. So that is why we now opt for non-parametric. Does he answer the question, sir?
Yeah, but this is like just a bird's eye view. Is it not better to do a normality test prior
of course, you know, this one is just in the process. If you look at it, in the process of running, you just say, okay, let us have discretely. You will have done the normative test before you even come here. Yes, I mean, you will have done all this common core of spin-off before you come here. You get the picture, sir? You will have done it. The person that is, before you take decision on inferential statistics, you will have done your descriptive statistics. You have all your summary, you have your percentages, you have your mean, median, mode, whatever. You have it, you can see the data, say, oh, there's skewness. That is why, for me to now, I want to carry out this test. Yes, I mean, so that is why, even when somebody writes proposal, I'm going to use this, I'm going to use t-test, I'm going to use ANOVA. That is proposal. By the time you carry out the study, when you are working with the study, the data, you explore the data, check for normality, you see, you now see that, look at, it's not appropriate for you to use the ANOVA. You now go and use the non-parametric counterpart. So you decide that what you now write in your final result will be different from what is in the proposal. The proposal is that you wanted to do ANOVA, but in the final, you now say, I did Kukawalis. That's just it. I think the question is answered, sir.
Yeah, it is.
Okay, sir. Any other question? Any other question?
You know, sorry, coming again. That
okay.
Monte Carlo, so my system was off and on during that period.
No, there's no big deal in that one. That one is that, especially when the sample size is large, you may want to see p-value with, imagine you have p-value also give you confidence interval of the p-value. That's what Monte Carlo does. And people don't normally use it. So, yes, I mean, it's not a common thing.
I say it gives you p-value of what, sir?
It gives a confidence interval. That's the only
p-value. Can you imagine?
Give you sir, it gives you
confidence interval of the p-value.
That doesn't make sense.
Oh, I see.
You know, this Monte Carlo you are talking, that's where they started statistics. That's where they gamble. They were gambling. That was how, in that place that they started, all those people that developed statistics from probability, that's where they started. When they call that place Monte Carlo. Okay, no problem. Any other question? Yes, let me go to, if there's no question, there are some things I want to, part of what we did yesterday. Some questions. You can stop sharing. So I think we can still, since we'll close very soon, we don't need to log out. We can still accommodate the thing. Can see you can upload it. We have to and put it on YouTube for you to watch. So let me go to. I think it should be under that factorial. Where is the slide? Okay. So there are some questions you were asking yesterday. That was Dr. Yes. Okay. Even the first one self was on orthogonal. Orthogonal. So the meaning of orthogonal is perpendicular, when something is at right angle, perpendicular. So in mathematics now, whenever two vectors approach one another in a perpendicular line at right angle, the product of the vector is 0. That's where the logic of this orthogonal something comes from. Orthogonal means perpendicular. Orthogonality has to do with perpendicularity. When something is at right angle to another thing, that's perpendicular. In mathematics, when two vector approaches in the perpendicular, they are perpendicular, the product of the vector is 0. So that is why you see that whenever two contracts, you multiply the contracts, the value of the contract for a particular, for all of them, and now add it together, give you 0. That is orthogonal. Does it make sense?
No, sir, it doesn't.
Others, does it make sense? Maybe I need to share it. Others, does it make sense?
I didn't get the explanation, sir.
Okay. Just wait. I need to share that because I didn't open that. Okay, this one now. Just a minute. Hope I will not. No. Let me quickly save the one that has this other one that I downloaded before I lose it. I didn't see it. So if you understand what I just said, just explain to her. Because I'm sure some other people understand what I said. Can somebody explain? Repeat what I just said about orthogonal, the meaning of orthogonal. Nobody to help me.
Like studies from two different opposing perspectives, so that looking at that data or the results from two or opposite perspectives, such that nullity. That means that really looking at it deeply. That's the way I agree you were talking. Because since that from perpendicular and the resolution is 0, that means in the statistical view now, you are taking two different perspectives. That's another way, looking at it from the other side, such that there is no bias. And look, that's the way I'm looking at it.
Okay, that's very great. Let me just share the, because I put it under the understanding orthogonal. Yes, under contrast. When it's orthogonal, yes, I explain it there. Okay, I've seen it. Because I didn't open the slide today. Yeah, look at it. Can we see? You know, when we talk about orthogonal and non-orthogonal contrast yesterday and day before yesterday, orthogonal means involving right angle or perpendicularity. In mathematics, orthogonality is the generalization of the notion of perpendicularity to the linear algebra or bilinear form. Two elements U and V of a vector space with bilinear form B are orthogonal when the product is equal to 0. So that is why when you multiply the weight for a particular group, the product should add up to 0. If the product adds up to 0, the contrasts are said to be independent or orthogonal. So, because you were asking what is the meaning of that orthogonal, they just use the word from mathematics. So, if you remember here, we talk about, you said contrast 1, contrast 2. Then for each of this group, placebo, low dose, high dose, you know, placebo was -2 for contrast 1 and was 0 for contrast 2. When you multiply both of them, it gives you 0. Now, when you multiply 1 and -1, because low dose was contrast 1 was 1, and was minus for contrast 2. When you multiply, it gives you -1. High dose was 1 in both 1 and 2, multiply, it gives you 1. When you add these 3 together, it gives you 0. When you add all these contrasts together, it gives you 0. When you add all this one, the contrast 1, for all the group now, for contrast 1 equals 0, contrast 2 equals 0. Even their product equals 0. That's why I say it's orthogonal. So that is what I can just say. But that's just explanation I just want to give, so that I give you more sense. When you were asking yesterday, what is the meaning of this orthogonal? Any other question concerning that? Then
Thank you, sir.
You're welcome. I wanted to explain something also. You know, I said yesterday, you see something like linear model, general linear model, and generalized linear model. So let me just explain. If you look at it, when we went to do ANOVA, the option was general linear model. You remember, Dr. Bako? You remember?
As compared to
Hello?
one way
Yes,
that
sir.
we did before.
You remember when you were going to do the ANOVA yesterday?
Yes, sir. We went for general linear model. Yes.
Exactly. Now, okay, because sometimes, let me just, is my SPSS open? Yes, it's open. Let me just share. I'll just show you same thing, because sometimes I like practical thing, practicalize it rather than just talking to the no. Where is the okay? Is it that I didn't click any of them? Let me click. Can you see anything? No.
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 Not yet.
No. I'm coming. Okay. I want to share. Okay, you can at least you can see this one now. What I just wanted to show is that this is the SPSS. When you say analyze, when we get to, can you see linear model? This one, generalized linear model. You'll be seeing sometimes people also they denote both of them with what do I call it? They denote both of them with GLM. Yes, I mean now. This one, mixed model. Mixed model means we have linear, we have generalized linear model. Mixed model, but now when we talk about generalized linear model or linear model, what it means is this.
You're going back to contrast. Okay.
Yes, I'm here. I decided to come back here for to explain. So it's a useful, whenever it's a useful framework, it's more like a equation for deriving continuous variable from factors or independent variable. The independent variable can be continuous, it may not be continuous, but the outcome is continuous. You see, ANOVA, ANCOVA, regression, all of them, they are under the general linear model. It's just an equation. That's why we know we have already said it more often and often that ANOVA and regression are the same. It is when we do regression, I will demonstrate it. So I know when we do regression, I'm going to run this ANOVA, even the same data you see, we run it as regression. Just to create dummy for it. Now, if you look at it, the outcome for either ANOVA or linear regression is continuous. Linear regression, ANOVA, the outcome is continuous. Look at all this one we are doing, weight, whatever. Now, it follows this, the data is equal to model plus error. Model plus error. If you remember, the model is from our ANOVA something now, the between is the model. Between is the model. Within is the error. Can you see now? Yeah. For ANOVA, the sum of square between is the, so the data is the total sum of square. The model, there is the sum of square between. The error is sum of square within, because that's the one that is not, your model cannot explain. Out of the total variance, your model can explain the between, but it cannot explain the within. That is the error. Thank you, the error. Or you can call it a extraneous factor, other factor that you are not studying. So it follows. If you say y is your outcome, you now have b xy. B xy is just telling you this x1 is the independent variable one, the first one, with their coefficient. We don't worry, it's when we get to regression, you understand the coefficient. And for B2, the second variable, you can have 3, 4, 5. That's why they put pk's as many as possible. This E is the error. Can you see now? So this one, BO is the constant. Remember, when we treat regression, we usually use the equation of a straight line. The equation of a straight line, you remember, A or BO, this BO is the same as A, is constant. Is constant. That is the value of x when y is equal to 0. Sorry, when yes, sorry, that is the value of y when x is equal to 0, the constant. When x equal to 0, the value of y. So this equation general linear model just talk about how you fit, you can use independent variable to predict the value of dependent variable. Then when you now look at the second one called generalized, yeah, the other one is general, but this one is generalized. So you know, most of these innovation challenges start with quantitative variables. The intelligent people will try to also extend it to categorical variable. I'm trying to pick that annotation something. The intelligent people try to use it for categorical variable. Now, generalized linear model, it extends that general linear model to a situation where you are not talking of continuous variable, so that you can predict something that does not even follow normal distribution, like categorical, anything. So that is where the logistic regression comes in. Logistic regression is not part of general linear model, but when you now talk of logistic regression, Poisson regression, many other things, that is generalized, that is extension of general linear model. For you to be able to use that formula, that same formula, the general linear model, you must have a link function. That is where the link function comes. And if you remember, some of us that were here when we did the workshop on comparing proportion, we did odd ratio also and relatively. We talk about log odd, and I told you that that is the origin of that logistic regression. Is when we get to logistic regression. For like a log odd is the Y link function for logistic regression in generalized linear model. Because logistic regression, we are predicting outcome variables that are categorical, they are not quantitative. So the general linear model is for outcome variable that are continuous. But for us to be able to use the same thing for even other that don't follow normal distribution are not continuous, they are categorical or whatever. Now you now bring a link function to add to that equation. Now call it generalized linear model. So that just so when by the time we get to regression, you get to understand the concept better. I think that's what I just said, because yesterday, because the reason is that when we were doing ANOVA, we went to general linear model, because ANOVA also is one of, because the outcome we are looking at is their quantitative outcome. I don't know if there's any question. Is there any question?
It's okay for the day.
Thank you so much.
Yes.
Good answer.
So let me just pause now, since there's no